All right, module 12. We're continuing now. Next module. So any questions concerning the syllabus, Manvito? Is everything quite clear? The data camp was okay, right? That's the 16th, yeah. So we have on the 16th, we have one session where it's just about presentations of the final analysis plans and the reports. And so you just prepare a short PowerPoint presentation with the idea to give a brief presentation on the topic and also kind of give you an opportunity. So you will learn presentation skills, right? And this is, I think it's a good forum. It's a good topic to speak about something you have worked on for a while. And it's also, research is a lot about presentation, right? It's getting more and more important. And I think this is just nice to also kind of get a little bit of feedback from your colleagues and kind of see what they have done, the analysis that they have done. So it's usually quite interactive. So it's actually a nice initiative. Then we have quiz 3, which essentially will mainly cover t-distribution and correlation, which is not too difficult. And I think none of you really had struggles with the formal quizzes, but it's been considerably easy. Well, that's good. All right. So we're talking today about statistical methods for correlation analysis and interpretation. That's usually whatever researcher gets exposed to quite early in the game. So these are things that are quite frequently used. I think linear regression is probably, next to the t-test, the most often used technique you will find in all publications. It's just really nice taking a step back. And I think this particular lesson is a good precedent to essentially go in the realm of multivariable regression. Because as soon as you do a simple linear regression, univariate with one variable only, the next step is what could hypothetically confound the association that you have seen. And the logical next step is to adjust this for additional covariates. And for this, you need to understand, obviously, the simple linear regression to the fullest. And this is essentially where I think this is a particularly interesting lecture. So we're talking about simple linear regression, we're talking about Pearson correlation and coefficients of determination, which is essentially the often quoted R-square, which kind of quantifies the strength of your association and the robustness of your model that you've developed. Even more important was multivariable regression, where it really kind of gives you a hint of how useful was the inclusion of this parameter and how much did it essentially hurt your robustness. Because fitting a model it's a little bit of an art form, and you may, if you go in more epidemiologically inclined classes, you will hear about directed acyclic graphs, where you essentially, where you essentially map out associations and hypothesized associations. So you essentially, you know from the literature associations between two variables, and the way these associate with each other will affect the direction of the coefficient in the linear model, and inclusion of those in the wrong manner can essentially harm your insights. It can be really problematic to actually adjust for the wrong parameters. If you have something that is called as an effect modifier, that actually once present in high magnitude, it inflates or it totally destroys your association, you have something that you have to deal with differently analytically. And this is why this is really important to not just blindly include covariates, but really put a lot of thought into what parameter you're including. So this is what we're going to discuss next week when we talk about multivariable regression. Today we're focusing on the linear regression. In its simplest form, in regression analysis and in the testing of associations, you compute the so-called Pearson correlation coefficient, which essentially gives you an idea about an association between covariates. The coefficient of determination is then the logical next step to that, and we will talk about it why. And we will briefly talk about non-parametric alternatives to the methods we've learned. And we went already to some extent in this direction with various other methods. So when we talked about t-tests and t-distribution, essentially you have a scale variable on the y-axis, you have a dependent variable that is a scale variable, and you have a binary variable on the x-axis. Your independent variable is essentially binary variable for a t-test. You have a group, you have a 0 and a 1 group, and you're comparing those two groups. Essentially, you have dependent variable on the y and independent variable, the two groups on the x-axis. So this is already the first step. Then you take a nominal variable with several levels, and you basically in the realm of building an analysis of variance, an ANOVA, which is essentially nothing else. Scale variable on the y-axis, nominal variable on the x-axis with several levels, right? 3 or more. So essentially, we went in that direction already. So we have a response variable or an outcome variable, and we have predictor variables of determining covariance. So inferences are performed on the response variable and is plotted on the y-axis. And in addition to that, you can make the same argument with binary data where the outcome variable is also binary, and so the response as well as the independent variable are both binary, and this would be, for example, the chi-square test, as we discussed it last time. So essentially, also your inference of a chi-square test is essentially also nothing else but a dependence or an association between two variables, which are binary in nature, or in several levels, in numerous levels. So then you have inference, for example, with 2 or more. So that's the t-test or an ANOVA. So t-test for 2, ANOVA for categorically or nominal variables. And you can graphically depict it, and you can also analyze it, as we have done. And today we're talking about the curious case of having a continuous variable and a continuous predictor. And there you have the luxury that you can depict every single point exactly how it presents in your data. And this is the so-called scatter plot. So this is a nice way to depict it, a nice way to understand your data, and to basically get a good handle on how the data distributes in the greater realm of your Cartesian system. So the applications are numerous. You have applications for lab parameters. How does one here does glutathione mediated detoxification associated with water disinfection byproducts? As an example, you can correlate literally all variables that you essentially can look at. You can quality of life associations, although quality of life usually doesn't distribute normally, so it's a debatable example. But you can have various examples that essentially use correlation analysis. Lab parameters and clinical characteristics, very typically ways of analyzing this. Scatter plot essentially is a y-axis and an x-axis. So you plot every data point in your data. You align every data point of one measurement or one individual. And all of these data points, all of these individuals need to be independent. And we talk about this in detail. So when you, for example, when you have repeated measurements, you need to use different methods. And that's important to keep in mind because that's something that is violated quite often. So down the road, you review reports or you review papers, you will need to keep in mind that repeated measures need a different regression method. This needs different analytical methods. You cannot do this with simple univariate or multivariate regression. They always need to be independent from each other. In the context of scatter plots and these associations, you can use correlations. And correlations essentially quantify the strength of an association. So you essentially, you have a linear relationship, and your null hypothesis is whether it differs from a flat line that corresponds with the mean of either variable. So that can be the mean of X or the mean of Y, but it will deviate to a significant level. And it's just like every other distribution, is also the distribution of the rho of the coefficient of the correlation coefficient, also dependent on the sample size, which is a problem when you have large sample sizes, because then every one of your correlations is going to be significant, where you again have to pay attention what is your outcome, and there you need correlation in the form of a regression, where you understand how much is that slope of this association, which quantifies the strength of this association and to what extent this has a clinical relevance or a clinical effect. The next problem is, and I have included a paper from Hill on when to possibly establish a probability of a causal relationship in association in observational studies. Because with correlations, you can establish correlations, but you can correlate with a good sample size, everything with everything. Not really literally, but you can correlate things that are not naturally causally related. And that is a problem. And this is why it's important to understand the association and understand the underlying hypothesis. Because with the enhanced data, for example, you will find with, I don't know, 10,000, 5,000 data rows, you will find correlations that not necessarily do have much meaning and much relevance when you really look at them in a causal relationship. So that's important. No causal effect is implied just because of a correlation. That's important to keep in mind. So examples of scatter plots are given here. So you have, as the most simplest case, you have linear relationship, where essentially you can fit a line through. Then you have nonlinear relationship, where this line would not be a line, but would need to be a function that has a certain mathematical function describing the shape of this association. But as you can see here, because you could fit a line through this without much differences between a possibly fitted line and the actual data point. And this is called a so-called residual. And if the residuals are small, you have an association, it's just not linear. Do you have a question? You seem to have, no, okay. So it's important to distinguish between linear relationships and nonlinear relationships. And this association also makes it so important, why you also always should create plots, because plots can be extremely insightful to hypothesize about associations. And that will drive your decision on which analytic method you will employ. Then you have, so you have linear, nonlinear relationships. You have strong relationships and you have weak relationships. So essentially strong relationships are very tight about this hypothetically fitted line, which essentially we will really fit it later in R. And then you have those where the so-called, if you fit a line through that, you have a wide range of so-called residuals. And the residual is essentially, you fit a line through that essentially has an equal distance from all of these parameters. It's called a least square correlation, where the squared deviation is as minimal as possible. So you fit that line in a way that the squared deviation from that line to that point, to that point, to that point, to that point, the difference between this predicted line and the actual data point is kept as small as possible. And this is how you arithmetically will approach this. But we're not going to do this. This is more down the road. But in its simplest form, a linear regression is a least square fitted linear regression. I'm mentioning this because there are different ways how you can essentially employ this. And this is, for example, a maximum likelihood estimation, which is a different approach, slightly more accurate in some ways of employment, but for the simplest form, fine to just approach it with ordinary least square estimations. So you have strong relationships and you have weak relationships determined by the residuals from the predicted function. And then you have examples where you have no relationships. And this is the aforementioned straight line. The straight line through your data that does not have a slope. It has no deviation in its slope from mean, from x or y, or y and x. So essentially that would be no relationship at all. So now again, the examples are manifold. You can use this for lab data, clinical data, neatly also for population studies. So you have population studies, you basically, and this is, I just want to emphasize this, you can essentially, and this is one of the examples which you could have also chosen for the final project, but we're doing this late in the game. So I remember my first intro course, I went to the World Bank data and I got country data. And you basically can, on this country data, you can build population health studies. So essentially you map those out in the exact same fashion, and you get a distribution and you can fit a line through that, and you can hypothesize about relationships. You can do that with scatter plots, and its simplest form with linear regression. So this, for example, is the example of diphtheria tetanus immunization compared to mortality of children younger than 5 years. And this is a simple study essentially that can provide a lot of insights. The sample size is small, but the estimates from each country are very solid because you get actual country data. This also goes in the direction of distinguishing between a population correlation coefficient and a sample correlation coefficient. So when you have a population correlation coefficient rho, you essentially have a linear association between two continuous variables in populations, whereas a sample correlation coefficient, you have an estimate of this rho, but essentially it's in its smaller form, it's a Pearson correlation coefficient, which essentially also follows a certain distribution, which is characteristic for a sample. Their sample size will play a great role. So the way to calculate this is comparable. So essentially you build for each entry, you have, you're building products. You have an xi, and you subtract the mean from that xi. So this is the individual x entry. You subtract that mean. You get by that you get a deviation. You essentially, with this deviation, you divide it by the standard deviation. So that's how you get the variability in there. And then you multiply it with the same deviation divided by the standard deviation of y. You sum that up and you basically divide it by the degrees of freedom. And that gets you to your correlation coefficient. So you have x, I, individual entry. You subtract the mean from it. By that, you get a deviation on the x-axis. You divide it by the standard deviation. That gets you the spread of x in there. And then you do the same with the y, and you multiply both together, and you sum that whole up, and you divide it by the entire sample size of both entries. So you don't need to multiply them by 2. It's just one individual gets one n spot. So you divide it by the degrees of freedom. So this is how you calculate the correlation coefficient. And this essentially gets you to an R. The R is essentially a directional estimate of the strength of this correlation, which can be either negative. -1 is the most minimal value, +1 is the maximal value. With +1 being like literally all data points on a straight line, the same with -1. Everything in between, and there you have the aforementioned residuals, where essentially you have a distance from that point to this line. And you're measuring these resistance on the y-axis. This is the deviation you're interested in to quantify your residuals down the road, because this is what you're predicting. And your prediction will essentially then in regression analysis will drive the magnitude of your residual. as mentioned before, the flat line is a correlation coefficient of 0, and you don't have a correlation at all. So the rho is unit free, as we can assume, because it divides. So you basically have a deviation, and you're dividing it by a standard deviation that drops the units, right? Then you multiply it and you sum it up. So that's how it becomes dimension free. It's always between -1 and +1, -1 strong negative linear relationship or inverse. Negative or inverse is the nomenclature that's being used. And then it's either positive or direct. So the closer to 1. The closer to 0, the weaker the relationship. So unless the rho is ±1, a high correlation does not necessarily imply a linear relationship. So you can still have a linear relationship, a non-linear relationship with a high correlation coefficient. Again, a question of the sample size, right? A high correlation does not imply a causal relationship, and that's the take-home message from correlation. And R is unfortunately very sensitive to outliers, which is nicely shown with this. Because when you look at this correlation, we don't have a correlation coefficient here, but these outliers are very strongly driving this relationship, right? Not only conceptually, but also arithmetically. So now inference on population inference on the population coefficient. So the null hypothesis is that the rho is 0. So it's a flat line. That's a null hypothesis. The alternative hypothesis is unequal to 0. It's two-sided. It's a two-sided test. And when the null hypothesis is true, the following test statistic is t-distributed with n-2 degrees of freedom. So this would be this approach, n-2 divided by 1 minus r squared. So this is your distribution. For this distribution, you also have a rho table. So there's a table actually for the correlation coefficient. But this will determine your critical values. So this is essentially how you convert this quote-unquote converted in a t-distribution. And you can use a t-table or you use the corresponding rho table. Yeah, and these are the Bradford-Hill criteria. And this is the paper that I added to the module because I think it's relevant. Because association does not equal causation. But there are some ways how you can essentially go in the direction to hypothesize causal relationships. And when you look at that paper, Hill did an amazing job outlining what needs to be met with your analysis to essentially make some assumptions about the causal relationships. Again, it's observational data, it's confounded, it has potential biases in there. You need to be aware of those. And these unaccounted factors render most associations or many associations not causal relationships. But you can do with replicating it in different population, changing sample sizes, doing random subsets, and various other techniques, you can kind of corroborate your assumptions about causality. So it's a good paper. I highly recommend it to review it. It's a landmark paper in statistics or epidemiology. So, any questions about correlation? Or was that clear so far? It's considerably simple, right? It's simple. The way you would report it is usually that you are talking about your correlation and you are reporting your correlation coefficient. In most cases, when it's a sample, it's an R. When it's a population health study, it's a rho. And you would report your correlation coefficient. You make a comma next to it and you state the p-value. Good. So the logical next step to that is regression analysis. And this is really where it's getting interesting, because now you're not only evaluating a correlation, now you actually go a step further. Now you actually say, okay, so I have now a dependent variable on my y-axis, and I have an x-axis. I have a parameter that has x and y, and I can predict my y by fitting a function through my scatter using my y and my x and this association with each other. And by that, I actually can predict my dependent variable with my independent variable. And this is actually where statistics get really, really cool in that one. Regression analysis is, so if you further your statistical education and you do a bias 2 class, for example, you will definitely have in-depth insights into regression analysis. You will learn a lot about that. And this is actually really, really a versatile tool that you can use. You can do repeated measures. You can do various things with more advanced methods. In case you're interested in some literature, let me know. I'm teaching an applied biostats class, and I have really good literature on that. So it's really, so the Wittinghoff, for example, which is one of the books that I'm teaching, this is a great resource. This is a really great resource. So regression analysis can be used to predict that value and explain the impact of changes in an independent variable on the dependent variable. The dependent variable is that we wish to explain, and the independent variable is the one that explains the dependent variable. In simple linear regression, you only have one independent variable, x. And the relationship is described by a slope, by an intercept, and by a random error. What does that mean? It means that we have a y, that's our dependent variable. We have an x, which is the independent variable. We have a beta 0. The beta 0 is our intercept. The definition of an intercept is, this is the value of y when x equals 0. So when we go back to the scatter plot, you go all the way to the left until you hit 0. And this where this function, this line hits the y-axis, because the x is 0, this is your intercept. The beta 1 is essentially the slope. The slope, and we will talk about this later, this is the change in y with a change of x, of 1x, of 1 unit of x. And then lastly, and this is quite important, and this is important to keep in mind, because this is what you then attack with your multivariable regression, because these covariates that you include, they help you to explain your residual error, your epsilon. So this is a residual error, a random error component. So again, y, alpha, beta, x, epsilon. So these are different ways how to depict it, but essentially the most common one is the one with beta 0, beta 1, and epsilon. So now in a sample regression, essentially it's the same way of depicting it. It looks a little different. So this with betas, as soon as you have Greek letters, always think population. As soon as you have normal Latin letters, essentially think sample. So characteristic, and this is also important for later classes, as soon as the y has a hat, it is a predicted y. Then you have an estimate of the regression intercept. This is the estimated beta B0 or beta. And that's the estimate of the slope. So same thing, essentially, and the random error terms. There's something to be said about the random error terms. The random error is distributed in a normal distribution around the mean of 0. So it has a certain standard deviation, but the mean of this is always 0, because the way you're calculating your fitted line, your function, arithmetically it needs to come to 0 because you fit it directly through your entire scatter. So when you use a least square method, you have here your residuals, right? So you have your line fitted, you have the individual data points, and these distances from the fitted line on the y to that point, this is your residual. This is your residual errors. So these e's are the residuals. And the least square is the line that minimizes the sum of the squares. So the sum of squares of this line, of this function, is minimized around mean of 0, normally distributed. Does not necessarily hold true for the variable itself. It's only the error is normally distributed. Good. The interpretation is the estimated average value of y when the value is 0. That's our intercept. The estimated change in the average value of y as a result of a 1 unit change in x is our b1, our slope. So now, when you take a step back, you have now sum of squares. You have sum of squares that are deriving from the regression. You have sum of squares that derives from the error. And you have sum of squares, which is the total sum of squares. So the total sum of squares is easy, right? That's your yi from your y bar. So that's the deviation from, so these are your squared deviations, which are those that you have calculated. For example, you remember the calculation of the standard deviation that we discussed briefly in the beginning? That's your total sum of squares. When you have a sum of squares error, here you have a yi, your individual entry, minus a y hat of I. So each individual gets, following that function, one predicted value. So that's an individual entry. So now this essentially gets you an individual specific entry. So each entry, each individual will have one error, one calculated error, yi minus y hat I. Squaring this gets you the sum of squares error. Sum of squares of the entire regression is now your y hat I, so all your predicted y's minus the y bar. And now, so adding this up gets you to the total sum of squares. And this becomes important because, so this predicted error, yeah. So total sum of squares measures the variation of yi around their mean. Error sum of squares is attributed to factors other than the relationship between x and y. And the regression sum of squares, the explained variation attributable to the relationship between x and y. This is what you were able to predict. So now the regression of determination essentially allows you to take the regression sum of squares divided by the total sum of squares. So it quantifies the proportion of explained variability over the total variability. So the explained sum of squares over the total sum of squares. And this will now be a value between 0 and 1. And this is essentially your R squared. And this is how much variation does your model explain? That's the definition. It's an explanatory, it is quantification of the explanatory capabilities of your model. So it's sum of squares explained by regression divided by total sum of squares. It becomes interesting because the correlation coefficient in univariate analysis, you can square it. The squared correlation coefficient will essentially be your R squared. This is not true with multivariate regression. Don't run into that. So this is important to keep in mind, right? Because you can't really quantify an R, and you need to be careful about assumptions you make about the associations. So examples of approximate R squared values, it's again the straight line, right? Minus 1 squared or plus 1 squared is both 1. Weaker relationships are closer to zero. Some but not all variation is explained by variation in X. So you basically have weaker relationships and various examples for that. And again, the R square of zero is a flat line. Again, the same null hypothesis. So there are a couple of assumptions that are now being made. One is a linearity assumptions. So you assume a linear relationship, and only under these assumptions you can employ regression in that format. Otherwise, you need a different mathematical function that you need to develop, which you can do with regression, but it's not a linear regression model anymore. Secondly, homoscedasticity. And this is essentially, we came across homoscedasticity with the ANOVA. You remember that there was a condition and assumptions we made in ANOVA that the variability within the groups would not exceed 20% from each other. And this is an extension of that, essentially, that the variance that you observe in your data should not differ with the magnitude of your X. So it should be constant across the entire magnitude of your explanatory independent variable. Then you wish to have some approximate normality. If not, you need to go into the realm of non-parametric statistics, or you log transform it, or you transform it in another way. So there are some transformation approaches how you can transform data, and you can still safely make the assumptions and still use that data in that fashion. Then interpretation gets a little bit more complicated, because essentially then you have a log transformed variable predicting another. And fourthly, so as the fourth assumption, that's also the most important assumption, and reiterating here, is that it's independent pairs of observations. So the correct expression is here seen on the bottom. It's y equals beta 0 plus beta 1 multiplied by the x plus the error term, where the error term is normally distributed with a standard deviation around a mean of 0. So that's the way how you would basically depict that. So the relationship essentially is that this beta 1 can also be calculated by knowing the correlation coefficient. In population, you can quantify it by multiplying the correlation coefficient and dividing the standard deviations. And you can do the same in the sample. So this is how the beta is related arithmetically. So it's sometimes interesting to know that. So these are things that don't need to be memorized for the quiz, and this is very deep into how to calculate things, but it's good to have the resource in hand and maybe like just save it, that you can derive from the standard deviation of your two covariates and the correlation coefficient, you can actually estimate your beta. If you're reviewing papers, for example, sometimes useful insight, can this actually really be? It's good to keep in mind. So results of inference on the null hypothesis, so beta 1 equals 0, and null hypothesis rho is equal to 0 identically. If x and y are converted to a set score, then beta 1 and rho are identically, yes, and the estimates of beta 1 and r are identically. So it's the same in a way. As an example here, we have the association between weight and height. And that's maybe an interesting example. So when you look at this now, and there's some questions on, so describe the relationship between height and weight. Is this a linear relationship, or is this not a linear relationship? It is to some extent linear, right? Can we actually quickly turn on the volume, what I'm transmitting volume, because I have some problems with it. You can hear it? Perfect. Okay, good. So the relationship between height and weight appears here to be somewhat normal. It's usually not normal, but that's also why there's a body mass index, right? Because it's not normal. So it's not traditionally normal. But nevertheless, let's assume it's linear and not normal, linear. I mean, let's assume it's linear. Let's look at this regression line. So slope at intercept is easy to find, right? And this is a very comparable kind of way of depicting this. You will always have an estimate, a standard error t value, because it's a t distribution, right? It follows a t distribution, and you have a probability value, you have a p value. You find the intercept here with the estimate that distributes around the standard error of zero, of a known magnitude. So essentially you would continue this to zero, there you would find your intercept, and you have along this intercept up and down, you have the standard error. So this would continue up until zero. So it's always zero, no matter how useless this estimate essentially is, because a height of zero has a weight of minus 105, does obviously not really make much sense. So if we are having an increase, so this is our slope, this goes with height. If we have an increase of 1 centimeter, the weight is gonna increase by 1.0176 kilograms. Every increase of 1 centimeter. And this is the same, right? Because the next question is, do we have homoscedasticity? And this is already where this gets a little tricky, because this is not a homoscedastic kind of relationship. There's clearly the variance is here in the higher ranges much, much greater, which also makes a lot of sense, because you have somebody who is tall, can be tall and can be at the same time overweight, but there can also be somebody who is tall, who is actually very skinny. So these are two different individuals, and you're assuming this line continues here infinitely in the same fashion. So this is an association that is debatable, right? So homoscedasticity probably not given. So does the data not provide a strong evidence that the increase in height is associated with an increase in weight? State the null and alternative hypothesis, report the p-value, and state your conclusion. Well, it is significant because it's a large sample size. But as said, it's not homoscedastic. It likely in the greater magnitude will deviate. It's going to get harder to explain. So I would not see it to be the strongest evidence. So this is why also people came up with different markers for this. And even the body mass index is highly debated at this point. And there are different markers that are giving much deeper insights in this association. So the correlation coefficient for height and weight is 0.72. Calculate an R-squared and interpret it in the context. And this is easy, right? So you just need to square 0.72, which is like something with 0.49, I assume. And it basically half of the variability is explained by the variability of your model. So that would be the interpretation of that. So the conclusion is it's a continuous outcome, continuous predictor. The Pearson correlation from -1 to +1 describes strength and direction of the association. An R-squared between 0 and 1 is the proportion of variance explained by the regression model. The regression coefficient is related to R by standard deviation of Y divided by standard deviation of X multiplied by the correlation coefficient. And this gets us to the end. So this is regression in a rather fast 45 minutes lecture. Any questions to that? Or was this considerably clear? I really like these slides. Yeah. I think once you sit down with the slides and you go through the slides again, there are bits and pieces in there which are neglected in many cases in many analyses, and it makes a lot of sense that you know what this. Yes.
You've done qPCR analysis, right? Like the data that we're getting from like the qPCR experiments, the real-time PCR.
No, we're not doing PCR, but
so for example, if we do one,
yeah,
we have like there's this expression which tells you the fold expression in case of some gene, for example.
Yes.
So in that, like there's one formula which talks about efficiency, the E.
Okay.
It tells you should take out it with the help of standard curve. How do you take out standard curve and efficiency together? Any idea?
Well, method comparison. Say this again. Efficiency.
Efficiency.
Efficiency. Okay. I'm not sure I'm familiar with this.
Efficiency for any reaction or any experiment.
Yeah.
Basically, which defines if you have performed the experiment properly or not.
Okay.
So that term becomes as the basis for your whole any reaction that you do or any experiment that you perform or any analysis that you do, that you're performing it properly or not. It becomes like a coefficient.
Okay. So I'm not sure there is, well, it could be some form of regression model underlying this quantification of efficiency, but it sounds like a quality criterion, kind of a quality assurance approach.
No, it's like quantitative.
It's
not a quality assurance approach.
No.
It's not. It's like a quantitative analysis approach.
Mm-hmm.
Because like the formula that I usually use is like which defines either efficiency is 1 or 2. If it is 1, it's not working at all. 2, it's working properly.
Okay.
So usually they say, like when I was studying about this through some studies, it says that like either you need to, if you don't know what you're performing, you find your efficiency that about a standard curve.
Yeah. So
confused, like a standard curve, if I'm performing, every time someone cannot create a standard curve for everything.
Yeah.
So how to like
so I would I think that standard curve is your quality criterion. And I'm not sure what the method is. I'm not familiar with the method. I'm not familiar with what is being done there. But usually, and I know this from different methods, usually you compare your assessed measurement. So that measurement that you did, you compare that to a standard curve. And only if it resembles the shape or in some other factors, it is comparable to the standard curve, you get a quantification of this resemblance.
That's something I got.
Okay.
How do you define efficiency through that?
Yeah, that I don't know. I would say it's a method that compares your assessment, your measurement to the standard
having
curve.
some values, getting its actual interpretation, what could be their values, like having some reading and getting what could there be actual values through standard curve is easy.
Yeah.
You just do a comparison to the slope and then you have the formula by iterating.
Yeah.
You use that. But then if you have something which defines efficiency of anything, any analysis that you perform, is that anything?
I don't know the methods you're performing, unfortunately. I'm not
in general also, not performing. Like in general, if you perform some analysis or you have some set of data and you perform some analysis, how efficient is it? Is there a way to check that?
Well, with regression analysis, your diagnostic, your accuracy of predicting something is quantified with the R-square. So this coefficient of determination essentially gives you insight of how well is your model performing. So that would be going in the direction that you're describing. But I'm not sure, I'm not familiar with PCRs. I'm not sure I can. Yeah. So efficiency is not really a term that is being used much in statistics. So it's something very specific to the method we're using, I think.
Kind of.
Yeah.
Specific, but like in general, also people talk about how accurate or efficient is it?
Accurate. Yeah. Accurate is the term. And this would be the R-square, yes. Because you're explaining this variability. And how well you're explaining the variability is giving you an idea of how accurate is your model. And this is true with all regression methods. I think that's probably closest to what you're describing. Yeah. Sorry, I can't be of more help. But if you give me some literature of what you're doing, I can do some research on it if that is helpful.
I have the data. I'm performing it these days. Like I'm doing the analysis. I've taken the R value and everything.
Yeah.
Getting confused with it. So it's a very simple thing. Should I just write a formula somewhere?
Please, yeah, absolutely.
I have a marker. I don't actually have a marker.
Hold on. I may have a backup marker somewhere. Here. Well, let's make use of that on the side. Is that a long formula?
It's a very simple formula.
Very simple. Okay, good.
So it just says ratio is equals to E to the power CTC minus CTT, which is this whole CTC, sorry, minus CTT is equal to delta C. So this thing is defined as efficiency, which according to the literature, if you don't know what it is either 1 or 2. 1 means it didn't work, 2 means it worked. But for any reaction, if you need to take it out or any gene like that, they say calculate with the help of a standard curve. And I'm not sure how to calculate for a standard curve. We are performing 10,000 reactions a day, and you can take out E every time.
There must be something that is measured.
Well, any analysis, like 99% of the time,
Yeah.
any analysis I do or like my colleagues do, they always take it at 2 because they think that the reaction is going to work. So they say let's say the efficiency let it always be 100%. But that cannot be possible every time. And if they're taking 2 all the time, it's not a good analysis to be honest.
Okay, so this difference here, CTC versus CTT, this is your actual measurement. So CTC is the control, or what
That's
is
the
this?
control.
That's the control, that's your test.
Yeah.
Okay, so this delta G is then basically your deviation from your measurement. Okay. And what is this? This is a concentration, or what is this?
No, in qPCR, what is the threshold cycle the amplification starts?
Oh.
So it's
Oh,
CTT and CTTC, like what is what the control we subtracted from the test. So we get the fold expression increase with respect to control. It's if it's higher or lower.
So the efficiency must be something very specific to the PCR.
To be honest, it's not. I studied about it's not. It's just this thing which is like efficiency.
So which other method is using?
There's a standard method for qualitative analysis, and that I don't use because I don't need to do that because I need to do comparison with respect to other genes.
Okay.
So I don't use that because that is for one regression analysis of one particular gene, if there is a fold expression increase or not for one with respect to one. But I have to do a comparison of 4 5 genes, so I'm a little confused with efficiency. It was mentioned that in the literature saying that efficiency of a reaction could be either 1 or 2, depending on what you assume the reaction to be.
Okay.
All right, what you assume the reaction to be.
Okay.
And there are 2 types of efficiencies. One is the assumption one is the geometric one.
Okay.
So the geometric efficiency, they define it as should be the one that you calculate with help of a standard curve.
Okay.
But my like what I think is like if I'm going to create a standard curve for 1, 2, 3, 4, 5, 6 different ones, then only I can get a standard curve.
Okay.
Like a straight regression line from its slope, I could calculate the efficiency for any 2 points.
Okay.
So, but the thing is, like, if I don't have this, and I assume it as 2, how accurate would be my results?
Not very.
So how is this being published everywhere? My questions are like it's really actually it's like if it clearly says you should know that assumption it should be either 1 or 2. 1 means it won't work, 2 it will work. This is not the point. Otherwise, you do a standard curve for every time, which is not possible and timely feasible as well.
So the standard curve, where do you have the standard curve from? Is that coming from the manufacturer? Is that something you established at the beginning of experiments?
We can do everything. Like standard curve for every reaction will be different. Any kind of gene analysis I'm doing, we have different genes.
Okay.
So I can't do that for one because like if I'm treating gene with someone X and one treat I'm treating with Y, I'll have to create a whole standard curve for both of them. Is that true? And I have to create a standard curve for both of them, and then I have to create a third standard curve with respect to control so that I could standardize.
I would need to read up on that.
Because I'm like concerned about efficiency, like if we and they clearly like assume it.
It's an assumption.
It's an assumption, but like how could an assumption at such a large scale be true all the time?
It's very specific to the method then. I'm not familiar with it.
No, I'm in general also I'm asked like if someone asks me to perform this and they just say like assume it didn't work, you take 1, assume it worked, you take 2.
So if it didn't work, how would you know?
It's a flat line.
Yeah, but then you know if it's either 1 or 2, there's a reason why that is a constant, right?
Yeah.
So it's not a quantitative. It's either 1 or 2. It's a binary kind of situation.
They say either take 1 or 2, or that's an assumption based efficiency.
Yeah.
But they say if you want to take it out, how efficient is it? Draw a standard curve. The companies like IDT, which make primers, you have Biorad, you have Kaizen. Everyone says that, like, take it at 2, just assume it.
Well, do you have literature on that?
Sure,
Forward me the literature. Be
I
happy
can
to
share
look
it with
into it.
you because it's
Yeah, sure. No, but don't give me proprietary things, but it would be interesting to know what it is.
yeah.
Efficiency. Sounds like something that a manufacturer would be interested in. I don't know.
No, manufacturers actually on their website they write this. If you just open this website for Thermo Fisher right now, just say qPCR analysis Thermo Fisher. They'll have 2 ways. One is assumption, one is geometric. Geometric way to see you have this graph, make a standard curve, calculate efficiency for that particular value.
Yeah.
That's fine. But otherwise they're like, let's assume it.
So
but when you have genes that don't work at all.
When you compare your standard curve to the assumed efficiency, how does it differ?
I don't do it because, like, I assume efficiency. I don't take a standard curve because every day I have different concentration of samples, different treatment levels. How could I create a standard curve each and every time?
So is the efficiency, is that dependent on the concentration? It is.
Yeah, because if the concentration is well, it is not just dependent on concentration, it is also dependent on multiple factors. Whereas if your reaction is taking place, first thing is if the reaction is taking place or not.
Yeah.
If the reaction is not taking place, efficiency will be 0.
Yeah, I'm sorry, I can't help you with this question, but yeah, the forward me literature on that, like that, I look at it. Sounds interesting. The inquisitive mind is very important. All right, so but let's carry on, and thanks for bringing that up, and thanks for sharing the literature with me. So if no question on regression and correlation, then we can do the example of the practice lab today, which is considerably easy today. Okay, so we have on canvas the enhanced subset containing age, gender, systolic and diastolic blood pressure. We are essentially taking the subset, we're bringing it in the in-class folder. There it is already for me. So essentially, you copy it in the same folder, and then you load it in your R. So again, this was R. Okay. Thank you. So we can, with R, you can always remove variables. And this is done here, right? So you essentially you have a decrease of, you have the DF. Everything before the comma is the row, everything after is the column. So if you have, just like you have here, you have 6 variables, and you only want 2 to 6, and you want to drop 1, you essentially you indicate that you want everything by leaving the spot before the comma empty. If you only want 2 of 6, you say you only want 2 of 6. And that basically removes one of the variable, the superfluous variable in the beginning. So we're recoding gender now as a gender factor. That essentially will, and we have done that already. I'm dropping it in the chat. just so you can move faster. As soon as I find the chart. That is essentially what we're doing now. So you can now, in the first step, in the practice lab, we are now being asked to do the following. So we're testing the association between age and systolic blood pressure in the overall population between males and females. We're plotting a regression function and an R2 for the overall population, males and females, and we conclude whether there's an association or not. And we are now calculating the pulse pressure. The pulse pressure is calculated as systolic blood pressure minus diastolic blood pressure and age. And if we include SPB, so this becomes already a little bit a multivariable regression that will show you how to do that. So essentially, we want to see whether there's an association between males and females. So essentially, firstly, we're going to compare systolic blood pressure, and this is just done with a t-test, right? So we're building up now our subsets, male and female. So now we're then comparing the blood pressure between males and females. Now running this essentially gets us to the difference, right? So the t-test shows us essentially that the blood pressure in males is higher than it is in females, by around 5 millimeter Hg. What is interesting in this context is that this difference, when you have a linear regression, you are essentially, when you have a binary variable, as that one unit change does essentially give you an estimate of that slope. So when you look now at the intercept, this is where the x equals 0. So male equals 0 is a female, and this 122.660 is the intercept. This is where x equals 0. So for females, the intercept is 122.660. The slope for male is now the increase from 0 to 1. So 122, and think about how the formula looks like. So you have an intercept plus your beta 1 multiplied by your x. If your x is male and it's 1, you're adding 4.722 to the 122. You are at 127.382. So you can calculate this through. If you do 122.66 plus 4.722, you essentially get the 127.382. This is important knowledge to have, because you can, and with binary variable, you can essentially estimate the difference between one versus another in an adjusted and unadjusted fashion. Okay. So this is basically the comparison between males and females. So there is an association between blood pressure and gender. Then we have, wait, let me drop that in the chat too. So what we're getting here is a plot that basically builds up an X and a Y axis, but no points yet. The points are added here by adding DFH and DFSPP. When you, in comparison to, as we usually did it by plotting right away, you have first an X and then after the comma and Y. And it's the same here, essentially. You do nothing else. So you basically, you plot age as X, and you plot the SPP as the second one as the Y. So you're only taking a subset, and this is what the bracket indicates. You only take the subset of what is female for X and what is female for Y. So essentially, this adds now the points in a certain pre-specified manner. So it shows you 0.2, PCH equals 2, indicates that all the points are going to be triangles. CEX 0.6 indicates that it's a smaller triangle than it usually would show by default. So it shrinks the triangle. And color red, COL red, is self-explaining red. If you do the same with males, you essentially can add now males in a different color. And this is nice to do that because essentially by that you can distinguish between both groups. So if you're building now the respective linear regression models, so you're building here with LM, you're building a regression model that basically is SPP as a function of age, gets you LM female, which is the linear regression only in females. So when you look at that regression, you have a slope of 0.6672. Whereas when you look at the male model, your slope is 0.332 or 3332. So the difference is that for males, they have higher blood pressures, but the association with age is smaller than it is for females. Why is that? Because females tend to have lower blood pressures than males, only in age. Once they are female, so there's a hormonal advantage that females have over us. So they have cardioprotective factors permitted by the hormonal levels circulating in their blood. And by that, they basically have a less steep incline of SPP for men, but females to have a steeper incline because they have it later at their age. So the increase is higher in relative terms. So this is then the first part of the assignment. Then we are now essentially adding the R squared from our assessment. So this is how you would add with you essentially you're fitting now all data points into a linear model. You get a summary, and this summary basically indicates that age has overall an increase of 0.51. So it was 0.66 in males, it was 0.33 in females. For the overall population is 0.51. And now we want to show on our plot that R squared, and this is being done with the text function. So text essentially allows you to show on the plot field, whatever parameter you want to show. So we want to show R squared, which is essentially at the spot 25, x25, y210. So this is how you position it on your plot. So you do that basically using the same coordinates that you would have for a point. With labels, you can basically paste whatever you want to paste, and you can paste here. So summary fit adjusted R squared allows for you to basically get, summary R squared essentially allows you to get the R squared. And all you do essentially with that formula, round R squared to, you're basically rounding the R squared to 2 decimals, and you're basically plotting it together with the R2 on your graph. So this is a fairly simple way to plot text on your plots in R. What you also can do with linear models. So any questions on that? It's fairly straightforward, right? So what you also can do with linear models is you can do residual diagnostics. And I'm gonna wait, let me drop that in the chat too. So you can, with residual diagnostics, you get a residual for each entry. So all your 1,000 individuals have residuals, right? You fitted a line through a virtual function, and now you get a distance from each individual point to your function for that predicted value. You can plot these, and then you get various plots. And with return, you can get through all those plots. So you have here, as the first one, you have residuals versus fitted. Residuals versus fitted allows you to see whether your data is fitted well and whether you have homoscedasticity. So this is a very nice and smart way to essentially look whether your variance changes over your entire magnitude of your parameter. If you are looking now at the second plot, here you have a QQ plot that essentially also gives you an idea about homoscedasticity and to what extent your data is normally distributed in an extent that you can actually use linear regression. If it's not, so you basically have these standardized residuals here on the y-axis as a function of theoretical quantiles that are derived from your model. If this deviates much, here it does in the extreme values, but if it deviates much, you could think of log transformation, for example, to shape your data in a more normally distributed fashion. For this particular example, I think it's considerably acceptable, I would think. Then you have here standardized, you have a square rooted standardized residuals versus the fitted values. That's a different way of looking at it. Residuals versus the leverage. So which residuals actually have a lot of weight in the model and have affected your standardized residuals the most. So you get kind of a weight in your data. So there are a few that do have a lot of leverage and have affected the models a lot. Others did not. The majority did not. So that is not something we should go into in much detail. The prediction of SPP using the linear regression function. So here essentially you can predict your blood pressure at 50. So as said, you can use this function that you're developing in the same fashion. So you have with when you predict it, let me drop that in the chat. So you can use the first line. So you have a fit one coefficients. So when you look at summary fit one coefficients, they're basically 1, 1 will be your intercept. And the summary fit one coefficients 2, 1 is essentially the slope for your age with 0.51. So multiplying that with 50, adding that to the intercept gets you an estimate of where a 50-year-old's blood pressure would be on the y-axis. So that's just one way how you can use this prediction. Yeah, so this was question 2. It's fairly straightforward, I found. Then let me also drop this in the chat. So we have here Q3. So here you have the calculation of the pulse pressure. So pulse pressure is an interesting parameter. So it's in epidemiological studies, one of the limitations you have is like sometimes you don't have the data you want to have. So the pulse pressure is kind of a way to quantify the arterial stiffness of an individual. One of the biggest problems where the blood pressure goes high is because you get a stiffness of the vessels in age called atherosclerosis. One manifestation of atherosclerosis is that the vessels get stiffer, and for that very reason, you have a difference between the systolic and diastolic blood pressure that is increasing. So the systolic blood pressure goes up, but the diastolic blood pressure does not. So this difference is the pulse pressure, and this essentially is a reflection of arterial stiffness. If you're plotting this, oops. You essentially get a considerably normal distribution. You can now plot this as a function of age. And you see that the pulse pressure is showing a little bit of an incline with age, which is hand in hand with what I just said. So when we fit that, we essentially get now here a significant increase of age. So it's a significant predictor. And with conf_int is a function that basically allows you to extract confidence intervals. Of note, conf_int, you can explicitly extract each limit of the confidence interval. So you can specifically target whatever confidence interval you want to extract, and you can use this for data reporting in a table, for example. It's a very useful function. If you do summary fit2, you essentially get exactly this association that we've seen. It's comparable to the systolic blood pressure, but it is different in standard error and in the prediction across males and females. With text, we can actually we can depict this on our plot, just as we did before. Maybe not. What's this now? 25 and 210. This is too much. So this is 25 and 150. It's actually outside of the range. So let's change this to 150. So now we have it actually on the plot. And then lastly, and this is nicely presented here, and I'm just dropping this in the chat. So this, you remember how I talked in the context of our graded lab 3. I talked about you could hypothetically populate your R demographics table directly in R. And this is one way how you could do that. Because essentially all of these functions are easily to be pasted in one cell with just a paste command. So if you are now depicting just this, you essentially get paste of the mean plus minus 20 point and the standard deviation, right? So you have it already in a reportable format. You can include a round function, and by that you can literally populate whole tables, and whenever you use a different data set, you use the same function, and it populates the whole table new within seconds. And that's just, it's an unbeatable advantage to have it set up in that way and format, because we did it by transferring it in Excel and working with it in Excel and transfer it from there in a Word document. Hypothetically would be the way how you get it in the table, in a type table 1, right? This is a way how you can actually do that in R and directly export it as a Word document, which is neat, very neat. And there are some other ways how you can do that. Did we ever talk about Markdown? You could hypothetically, all of this could go in a Markdown. So if you go here and on the plus, you have here R Markdown. With R Markdown, you can do something very nice. You can either do HTML, PDF, or Word document directly. And you can create this in R. Easily, you can also make slide presentations. So you can do PDFs that you can just put on a beamer. You can do HTML, PowerPoints. You can create PowerPoints with Shiny. You can do Shiny presentations, Shiny documents. So there are really neat ways to do. So when you go here on PDF, so I'm just flagging this. PDF requires the installation of MikTeX, so that's a LaTeX application, which makes it a little tricky. But essentially, you can. I have it installed. But if you have here a document, you create these little chunks where you have your formula in it. And you can execute this. When you do include false, it will not show. And then you can here write, and you can do another function, and there you just show the result of your regression model. You can include plots. And now down the road, the only thing you need to do, you need to knit the whole thing. And once you knit it, let me close, okay. So you can basically create this within seconds. And the output of that will be a PDF that you can then share with collaborators. And it's the same principle. So the more you can present in such a document, you can update it within seconds. And this is gold. If you're writing reports, for example, and you get a new data set in, or you get additional data entries, you just update your source data file, or you change your source data file, you get it out as a report, as a PDF report within seconds. Unbeatable approach. So that's really something I would like to flag to you, since you both are more analytically inclined, and also for everybody watching this recording. Yeah, so this is Markdown. And yeah, and these are the ways how you can basically depict data in whatever format you want to depict it. So this is mean plus minus standard deviation. This is median plus 25th to 75th percentile. This is any estimate from a linear regression model with a 95% confidence interval, lower limit and upper limit. So this is essentially how you quickly can present this and nicely embed it in a table or in a Markdown document. Yeah, so I'm going to post this and have fun with it. I highly encourage you to go line by line through the code and really make sure that you. Are there any questions on that code? Good. Then I can conclude for today. All right. Any questions, David?
No, Professor. Thank you for your class. See you next week.
See you next week.